ECOSF, and UISMS. The EcoScience Foundation is a specialized agency of the Economic Cooperation Organization, an intergovernmental entity with 10 member states, including Afghanistan, Azerbaijan, Iran, Kazakhstan, Kyrgyzstan, Pakistan, Tajikistan, Turkey, Turkmenistan, and Uzbekistan. Its mandate is to promote science, technology, and innovation among the ECO member countries. The Union of Iranian Societies of Mathematical Sciences, or UISMS, is a non-governmental, non-profit organization which was established as collaborative efforts of several esteemed mathematical societies and scientific associations to synchronize their future plans and actions for improved outcomes. The primary objective of USIMS is to assist all members in facilitating the study and advancement of mathematical sciences within the country. IPKI is an organization committed to making the world a better place by promoting science education, fostering intellectual curiosity, and bridging gaps in access to quality learning opportunities. Today's session takes us into the intriguing world of mathematical optimization as we explore the moving sofa problem, a deceptively simple yet unsolved problem in geometry that has captivated mathematicians for decades. And to guide us through this topic, we have with us Dr. Abdullah Malik, a mathematician with an extensive background in pure mathematics and its intersections with quantum mechanics and algebraic geometry. Dr. Malik completed his undergraduate degree in mathematics from ComSat's Institute of Information Technology in 2012, where he worked on quantum computing via quantum optics. He then earned his MPhil from Quaid-e-Azam University, focusing on the interplay between vector spaces and Hilbert spaces in quantum mechanics and general relativity. In 2023, he completed his PhD at Florida State University under the guidance of Dr. Tyler Foster, an algebraic geometer, where his research explored the connections between infinity categories and graph neural networks. Tonight, Dr. Malik will take us on a journey through the history and mathematical landscape of the moving sofa problem, from its formalization to the most recent proposed solution. Without further ado, let's welcome Dr. Abdullah Malik.
Thank you, Afsa, for the introduction. I'm happy to be here. Thrilled to be back with so many different people, especially from my past university. It's an honor to be here. I was a student just like you guys, just like Hafsa told everybody. Just one slight correction. I completed my PhD back in 2024, not in 2023. I mean, I wish I had completed my PhD sooner, but I was in 2024, not in 2023. Right. So I'm not gonna take too much of your time. Hopefully, I might finish in like 40 minutes or so. But like Hafsa said, I'll be talking about something called the moving sofa problem, and it's a problem that's been on a lot of mathematicians' minds because it's such a simple problem, but it's such a geometric problem. It's such a practical problem that but one that has evaded solutions until fairly recently. There's been a renewed interest in the moving sofa problem because of a proposed solution that came back in 2024. It's still a proposed solution, hasn't been peer-reviewed yet, but the looks of it looks promising. So let's just basically get into the details for the moving sofa problem. So we are going to work in the Cartesian plane R2, the usual X and Y axis that you know. And so what happens is we're going to define a hallway. So it's basically this highlighted set that I have over here. The interval from negative infinity to 1. So your x-axis go from negative infinity all the way to 1. And your y-axis go all the way from 1 down to so I think I have this backwards from 1 to infinity. No, it should go from 1 to negative infinity to 1. Yeah, I have this backwards. Anyway, so basically you have to have this highlighted part. You think of this as a hallway. It's infinitely long in this direction and this direction. Of course, it doesn't matter if you should have it an infinitely long hallway. What matters is that in this intersection, you have a 1-by-1 hallway in which you need to take a sofa and you need to turn it in the hallway and move it down. And it's basically the problem. All right. The dimensions for 1-by-1 over here are fixed just to make the problem a little simpler. I mean, in principle, you might have different dimensions over here, but the problem is defined this way to just make sure that the dimensions are like a little simpler to manage. The numbers are a little simpler to manage this way. So Leo Moser, back in 1966, basically asked, "What's the largest sofa that you could move through this hallway?" Right. This was his problem. It was posted in Siam Review. Basically, the Siam Review is basically a collection of questions that goes through different possible solutions. It's like a proposal for like, hey, here's something interesting that you might want to look at. It's like it used to be a popular magazine back in the day, but now it's like a serious publication. But back in the day, it was mostly like a popular magazine. It's like Scientific American. Um, so the idea is you basically consider a two-dimensional hallway because maybe the sofa is just too heavy to lift. You can just maybe just push it. So it's enough to consider a hallway that's two-dimensional. Um, the initial proposal said, well, the three-dimensional version is not really necessary to consider because you could just maybe stretch your sofa up vertically, or and then you're basically looking at a prism or a cylinder, just like they're worded over here. So if you can answer the problem in two dimensions, you basically answer the problem in three dimensions, so to speak. But I kind of have a disagreement with that. So we'll see how that works out. Okay, so there are two formal statements that we can look at. So if we look at the first statement that says, what is the planar shape of maximal area that can be moved around a right angle corner in a hallway where the hallway has a unit width? This question is different than asking, what is the largest area of a shape that can be maneuvered through a unit per hallway? So the difference between the first one and the second one is, in the first one, you're asked to determine the shape. And the second one, you're basically asked to start with a fixed shape and then determine what the largest area can be. The second question was basically answered by Kellis and Dan Romick back in 2018. Dan Romick has been seriously considering the SOFA problem for over a while now, and he came up with really good proposals, but essentially the second solution still did not answer why do you need to consider that shape. So 2018 was the closest that people came to solving the moving sofa problem, but it has still been unsolved since the initial proposal. So the first thing that we can consider is, of course, a unit square. So you take a unit square, you move it across the hallway horizontally, and then downwards. That just basically works, right? So that's like the simplest solution you can imagine. The error for this is, of course, 1 because it's a 1x1 square. The question is, can you do better? Can you have a bigger shape? And then the answer is, of course, we can. So in the second case, what you can do is consider a semicircle. So I guess everybody in the audience will probably know that the area for a semicircle is pi r squared over 2, where the half comes from, basically taking a circle and squishing it down to half a circle. And so if you take the radius to be 1 unit, what happens is when you hit this point, you can easily rotate your circle because it has a unit radius, so there's no trouble in rotating the circle and bringing it down. So now you've improved your area from 1 to 1.57, right? Okay. And these were the initial proposals. They were seemingly easy figures that you could come up with, and it took quite some time for somebody else to come up with a figure that was a little more complicated than this. Now, John Hammersley, 2 years later, came up with a more complicated shape where the area was improved by from 1.57 to 2.21 approximately. His problem was posed in an appendix to this audaciously titled publication. It says, "On the enfeeblement of mathematical skills by modern mathematics." So basically, John Hammersley was a big part of the new math debate that was happening. Essentially, the debate was, should mathematics focus on problem solving, should it focus on abstraction. I think it was during this time when the Bourbaki school was taking shape and formalizing a lot of mathematics, and John Hammersley was seriously against this formalization. So he published his problem in this publication, and later on came up with a solution. He was quite spot on the upper bound for the area of the object, which is 2 root 2. But now we know that his upper bound is like way off. It is an upper bound, but it's not the upper bound is not tight. In fact, John Hammersley, the A number that he has over here, I'm going to show you how to construct the shape, and it's a really elegant shape. So what John Hammersley did was basically he took the semicircle, right? You break it into half, you kind of stretch it, fill it in, and you want the rectangle that's in there to be, of course, the length is going to be 1 because that's radius of the circle, the semicircle, sorry, and you want the width for the rectangle to be 4 by pi. And then you carve out another semicircle, and you want the radius to be root 2 by pi. Once you do that, then this object that pretty much looks like a telephone. I don't know if I'm too old to remember what a telephone looked like. I don't know if the audience over here knows, but in the olden days, this is what a telephone used to look like. Um, I don't know if John Hammersley was inspired by the telephone, but this is the sofa that John Hammersley proposed that has an area of 2.21. And this was proposed back in 1968. And for a long time, this was the only best-known solution that people knew. Now, the way this works is you're not just rotating your sofa, you're also kind of pushing it. So you can see you're not just rotating, you're kind of pushing it down the way. When you carve out the semicircle from the rectangle, it helps you maneuver the sofa to the hallway. I don't know if any furniture company will be interested in making a sofa of this type because I guess the sitting would be very awkward. You'd have people with their knees touching, but this is a good shape that had a big area compared to the previous best, which was 1.57. Along came Gerber. So from 1968 to 1992, there was no progress on this problem. Now, Gerber's sofa looks pretty much the same as Hammersley's sofa, right? It still looks like a telephone, but there's a subtle difference. If you look closely over here, I have a bigger picture later on. The edges are like curved over here, right? Now you can of course move the sofa around, but Gerber's idea was to not rotate the sofa, but instead just rotate the hallway, right? I mean, that's something that you can do in the real world. Of course, you can't rotate the hallway if you want to move a sofa, right? But I guess mathematics allows you to do that. So in here, what you're doing is basically moving the hallway itself, right? And what that allows you to do is basically construct the shape on the inside that you need that allows you to perfectly maneuver the sofa, right? So you're not focusing on the sofa itself, you're focusing on the hallway, and the movement of the hallway describes the actual shape that should go into it. Of course, it takes insight from Hammersley because Hammersley decided as well, if you cut out a semicircle from here, then you can rotate the sofa easily. Here is Hammersley's sofa. So there's a slight cut over here that you'll notice, right? And you're rotating the hallway in the back. These lines that you see are lines that you see when you rotate the sofa. I have a good animation over here that I like to play. I put the link over here. Can everybody see the my Chrome?
Not yet.
Okay, hold on. Let me just stop sharing and share my window. How about now?
No, we see the slides.
Mhm. Okay, there we go.
Yeah.
Yeah, okay. So if you go to this link, you can basically play with these different numbers over here. You can move the hallway left and right, up and down. This is supposed to move the hallway up and down. This is supposed to rotate the hallway, right? So once you play around with these numbers, you have a different parameters over here that you can play with, and once you're allowed to do that, that basically helps you determine the shape that needs to go into making Hammersley sofa. Um, I have an animation over here that shows exactly what's going on. I mean, you can play with this GeoGebra tool on your own, and ultimately, what's going to happen is you're going to notice that Gerber sofa really is a good proposal that sort of seems like it should be the optimal area because you're not focused on the shape of the sofa. You're focused on the actual hallway that can fit that sofa, right? So it's turning the question on its head. But once you are able to carve out the shape of the sofa, and then say, well, this looks like it might be the best solution. For a while, people really thought that this would be the best solution, and the reason was because uh, it satisfied something called a local optimality condition. So if you're taking calculus, you're trying to find the local extrema for a function. If you found lots of different local extrema, then from all those local extrema, you can tell what the extreme value is going to be, right? If you know where the solution is maximum in small places, and you know all the small places that there are, you know the biggest there can be, right? So what this construction essentially does is proposes a local optimum. It says that if this is going to be your shape, then it has to be the biggest one, in a sense. So, and people believe that for a long time that this really is the best we can do. And a lot of people tried different approaches, but ultimately came down to a shape that looked really much like Gerber's sofa. Um, here is here's basically Gerber's sofa. It's built from a bunch of different shapes. There's one arc over here, there's one semicircle over here, there's one arc over here, straight line here, arc, so many different arcs. Gerber basically came up with these four different equations and solved them for different values and put these curves together to make a sofa. Now, if you have the system is nonlinear, right? So one way you can solve this such a nonlinear system is by a computer program. This doesn't give a closed form curve that you can use to decide what the shape for the curve should be. It only gives you different pieces that you can put together, right? So this was a good solution, but it wasn't the optimal solution. But it was one of the best solutions that we've known since 1992. And the area for this sofa is 2.22 compared to 2.21 for Hammersley. Marginal improvement, but nevertheless, for a long time, this shape was considered the best possible shape that we have. I want you to basically take note of this path over here because this path is going to be important in the actual solution that we're going to talk about soon. Any questions thus far?
I think it is very clear so far and very, very intriguing. Like it's that suspense has been developed that what is going to happen next.
Okay. So now, Jinbaek, basically, he was a PhD student when he published his solution, right? His paper, it's up on archive. I have the references in the end of this presentation, and I'm going to share the presentation with the organizers so they can disseminate it. But Jin Baek was a PhD student, and he insisted that he wanted to solve the moving sofa problem for his PhD thesis. And his supervisor said that this was the first time that he took up on a student who wanted to work on a problem that was really far from his expertise. Jin Baek had a really hard time finding a PhD supervisor to guide him through, but Jin Baek basically came up with a really elegant solution. His paper is up on archive. You can read it. This was published back in November 2024. If you've taken a course in Calculus 3, I think you can basically sit down and work through the problem. The paper is like 100 or so pages. It is long, but it's really well written. All the definitions that you'll need, all the images that you'll need, they're in the right place. they're referenced the correct way, the way you would expect them. I think it's really reader friendly, and if you could just sit through and work through it, it's a good paper. One of the reasons why I wanted to talk about this problem was because I want to read the paper myself. I've not read it completely, but just by going through what I've done so far, I think it looks like the Jin Bai really is on the right track because he came up with something really elegant. So what it did was basically broke down the proof in 3 different steps. So the first thing that it says did was you basically need to find basically need to pin down the shape of the sofa that you need. All right. That's what S sub max is going to be. So you want your sofa to satisfy 3 conditions. You want it to be monotone, balanced, and you want to have a rotation angle of 90 degrees. The rotation angle is basically the maximum rotation that you can give to an object because you have an L-shaped hallway, right? You want to be able to rotate your object up to 90 degrees, right? That's what the rotation angle is over here. The first and the second condition basically, so you want your sofa to be monotone. When you say monotone, it's basically that as you keep on rotating the shape, rotating your hallway, you want your sofa to be incrementally becoming a better and better shape, so to speak. That's kind of like the idea over there. And number 2, you want your sofa to be balanced because what this states is it's a technical requirement for the symmetry of the sofa. Now, all the shapes that you've seen so far, they're symmetric this is of course symmetric about the y-axis. The square is of course symmetric about the y-axis, and Hammersley's sofa is also symmetric about the y-axis, and Gerber's sofa is also symmetric about the y-axis. So you want your sofa to be balanced. It's basically imposing a strict condition on the sofa to be symmetric about a particular axis, so to speak. It's more than that. It's strictly more than that. It's a stronger condition. But the rough idea is you want your sofa to be symmetric, and the reason is that because you want to be able to move it. So the rotation that you do on one side should be what you should do on the other side. It's roughly the idea. The second thing that when Jin Bai decided what the shape of the sofa should be, he also addressed a lot of speculations on this construction over here, right? I mean, when John Hammersley and Gerber came up with their constructions, sure, they rotated the hallway, but they rotated the hallway in a very special way, right? What Jin Bai did was he said, okay, you can rotate it any way you want, as long as it's up at most 90 degrees, and you want your sofa to satisfy these conditions. That allows you to bring in more shapes than Hammersley's sofa and Gerber's sofa. So the first thing that Jin Bai did was expand the possible shapes of the sofa that you can consider, and then brought them down to Gerber's sofa. Okay. The second thing that Jin Bai did was he showed that your sofa, the maximal shape, had to satisfy something called the injectivity condition. Now, the injectivity condition is basically saying you want to consider a curve that starts at the origin and traces out a path as you move your shape along, right? So the injectivity condition has to consider this arc. And you basically don't want your arc to intersect itself at a different time period. You don't want your arc to be self-intersecting. It's kind of like saying that when you're moving the sofa, you don't want to move it back and forth, back and forth, back and forth. This is a technical requirement. It might not seem feasible or realistic to say, well, I can move my sofa forward, but I want to move it backwards a little bit, like tweaking and forwards and backwards. That's how we move sofas around in hallways, right? But the reason you want to have this injectivity condition is because you want to basically be able to take all those shapes down and bring it down to one number. I bring it down to one condition in a injective manner. So because all these shapes are geometric, it's really hard to work with geometric shapes if you have a bunch of numbers floating around. What the injectivity condition does is basically breaks this shape down into one single number, right? Now, with that one single number, you basically establish different areas, so to speak, right? So the injectivity condition has to do with the area for the object, but it's not exactly the area for the object. Now, once you have a shape and once you have a path that the shape takes, and you're mapping those two objects into a single number, you work with that number. Jin Baek was able to show that with a sofa that satisfies these three conditions and the injectivity condition, you basically construct a domain for your object, and then this second bullet over here, what it's doing is basically taking your sofa, right, and constructing a polynomial of degree 2 two variables. This is what a quadratic functional is. And it's converting the shape of the sofa to a single polynomial. And once you reduce your geometric object to an algebraic problem, right, the solution becomes really easy. That's essentially what the people did over here. But these problems, they require computers to solve, right? You can't do them by hand. On the other hand, what Jin Baek's solution does is takes a really hard geometric problem, reduces it down to a problem in algebra in an injective way. And because the mapping is injective, what that allows you to do is really focus on optimizing that polynomial. So if you're taking a course in calculus 2, it's basically like finding the global max or the global minimum of a polynomial. That's essentially what the problem boils down to. Sure, it's not a polynomial of a single variable. It's a polynomial of degree 2. So you have to use tools that are a little more advanced at calculus 1. But if you're taking a course in calculus 3, you can easily follow through the solution for Jin Baek. It's essentially taking a derivative, setting equal to 0, and then solving that for that derivative. Once you are able to establish the domain for that polynomial and show that it satisfies something called concavity condition, the problem is basically solving the polynomial. And once you can solve the polynomial, you know what its local solutions are going to be. And once you know what the local solutions are going to be, because the polynomial is concave to begin with, you'll know what its optimal solutions are as well. So it's basically like saying, I know what all its local maximas are. Because I know what all of its local maximas are, I know what its biggest maxima is, what its extreme value is. Essentially what Jin Baek did. I also like to point out that with this setup, what this setup does is you can choose your rotation angle to be what you want to be. So because the actual setup asks for an L-shaped hallway, right? You want an angle to be 90 degrees. But realistically, you might have a hallway that's not perpendicular, but that's a little angled differently. If you have a hallway that's angled differently, the setup for Jin Baek also works precisely for that. You might have different numbers, but you can basically use the tools developed by Jin Baek to solve for that problem as well. All right. Any questions on this slide? I know this is a little packed together, but I have to pause and see if there are questions. All right, let's move on then. So of course, the moving sofa problem is not the only problem that mathematicians have come up with. There's also something called the piano movers problem. And what it says is you want to move a piano in three-dimensional space, right? And so this paper basically produces an algorithm that can that asks you for the number of vertices that you want in a polygon. A polygon is basically a three-dimensional shape. So a pyramid is a polygon, a cube is a polygon, n is the number of vertices for that polygon. So if n equals 4, you basically have a pyramid with a base. It's a triangle. If you have n equals 6, then you have a cube, right, and so on. So if n is the number of vertices for the polygon, this algorithm basically says that it's going to take it's the algorithm has complexity of n to the 5. It's a polynomial degree complexity. And so it's an efficient algorithm that basically says whatever your shape is, as long as it has n vertices, you can move it to a complicated hallway in at most n to the 5 steps, so to speak. So this is one generalization that was proposed back in 2000, really fairly old. Another proposal basically asks a different question. So instead of an L hallway, you have a more realistic Z hallway. It's called the ambidextrous sofa because you don't want to rotate your sofa one way. You also want to rotate your sofa the other way as well, right? And so the solution to this, it would basically require your sofa to be symmetric about the x-axis as well, right? Because you want to rotate your sofa both ways. I mean, if you in your head, if you picture that you can basically move a unit cube over here, no problem. But you start with moving a semicircle over here. Sure, you can move it down here, but then you'll be stuck over here because you won't be able to rotate it. You want your shape to basically be symmetric about the x-axis as well. So this was a shape that Dan Romick came up with back in 2018 that solves this particular problem. And the idea is essentially based on the idea of Gerber, where you're rotating the hallway itself, but instead of coming up with 4 equations like Gerber did, Dan Romick came up with 22 different equations and solved them. But the good thing about Dan Romick's solution is that his solution does not use a computer program. You can pretty much write down the shape of this object in a closed form. Right, so that's the nice thing about Dan Romick's solution. This is one sofa. I don't know if it's really a practical sofa. Maybe it's a 2-seater sofa, but it is a sofa nevertheless, if you just maybe stretch your imagination up a little bit. I have my own proposals. So this might be a good project for an undergraduate. Instead of focusing on a 1-by-1 hallway, you can basically have an A by B hallway, right? Just to make it a little more realistic. And the solution is not going to be extremely earth-shattering because you're basically taking up a matrix transformation and rescaling everything back to different dimensions. All right. So if you're taking a course in linear algebra, what you basically will do is map your hallway that has different width and height, or different length and width, into a 1-by-1 situation by using this transformation. Solve the resulting system by using the proposal for Jin-Baek, and then just remap your object back to the inverse transformation for this, right? But I think if it's instructive to basically not work through this transformation, but rework the details for proposed by Jin-Baek using this modified hallway. Then in that case, you're basically working through a different problem, but this way you would essentially know how the solution that Jin-Baek came up with works. Another instance that is floating around but has not been formalized yet, I think I could find a paper that basically says, okay, here's the problem, what is the solution? You go to different blog posts and you'll see like variations for the 2-dimensional hallway to the 3-dimensional hallway problem. So basically, same situation as before, but now you don't only have an L-shaped hallway, you also have a 3rd dimension poking out. It's infinitely long in the height axis. And you can, of course, move a unit cube down the hallway. But as soon as you basically introduce a semi-sphere, right, a hemisphere, you run into trouble because then you might be able to rotate it one way, but you can't rotate it in the other way. So what you would need is not a semi-sphere, but you would need a quarter of a sphere, because that you can rotate in the other direction that way. So the situation is a little different in the 3rd dimension. So based on this logic, I would expect the solution for the 3-dimensional version to be something that looks like Gerber sofa, but instead of the Gerber sofa rotated 180 degrees, maybe it's a Gerber sofa that's rotated by 90 degrees to solve this problem. But it might be an interesting problem to work with. One final problem that I would propose is, let's just consider an n-dimensional hallway, right? So now you don't have just 3 axes, you have n axes. And I think the solution to this is not going to be straightforward. I mean, you can use the tools developed by Jin to essentially map this problem down to a polynomial of degree n with n variables. But then my intuition says that you're going to run into trouble because the geometry that we know in 2 dimensions and 3 dimensions breaks down in higher dimensions. So it will be interesting to see the dimension at which the generalizations start breaking down, number one. And number two, if any, the shape might be a little different. The reason I say that is because this might be counterintuitive, but the area of a hypersphere, as you keep on increasing the dimensions, becomes 0 instead of exploding onto infinity. So in I don't know, in 1,000 dimensions, things are like really different compared to the dimensions that we know in 2 and 3. Here are some of the references that I've used, and I'm happy to take questions.
Well, thank you very much, Dr. Abdullah. It was a very, very interesting and inspiring problem. So before allowing the questions, I would just like to make a comment about the mode of communication. So we actually, since our co-hosts include international organizations, so that's why we encourage English as a means of communication. But since I can see that the audience primarily includes Pakistani audience, so they are encouraged to ask in Urdu as well. So the reason for using English is just to कि अगर international participants हैं, so they should not feel left out. But since we are all from Pakistan, so Urdu में भी सवाल जो है वो पूछ सकते हैं. The purpose is कि आप सवाल करें. So कोई ऑडियंस में से क्वेश्चन है तो they can ask to unmute. So मेरे 2 बेसिकली सवाल हैं डॉक्टर अब्दुल्ला. एक तो थोड़ा जनरल नौयत का है. फॉर एग्जांपल आपको शायद मालूम हो कि 2022 में जो फील्ड्स मेडल था उसमें जो एक रेसिपिएंट थी वो मरीना वियाज़ोव्स्का थी खातून, और दूसरी खातून थी जिन्होंने ये जीता फील्ड्स मेडल. और उनका जो प्रॉब्लम था वो सफ़ियर पैकिंग को उन्होंने सॉल्व किया था 8 डायमेंशंस एंड 24 डायमेंशंस. सो मुझे आपके प्रॉब्लम में थोड़ी सी वहाँ से सिमिलैरिटी. सो सफ़ियर पैकिंग भी अपनी जगह एक बड़ा इंटरेस्टिंग प्रॉब्लम है कि वहाँ जो है कि एक बॉक्स में आप कितने सफ़ियर्स पैक कर सकते हैं. और इंटरेस्टिंगली जिस तरह से हमारे फ्रूट वेंडर्स वो रखते हैं तो वो एक बड़ा अच्छा वे है उसको रखने का. सो डू यू थिंक कि इस प्रॉब्लम का, मूविंग सोफा प्रॉब्लम का, और क्या ये सब्जेक्ट डिस्क्रीट ज्योमेट्री कहलाता है आपके, मतलब ये किस मतलब ब्रांच ऑफ मैथमेटिक्स में हम इसको करें?
और ज्योमेट्रिक ऑप्टिमाइजेशन में ख्याल से ये लाई करेगा, और स्फीयर पैकिंग प्रॉब्लम भी ज्योमेट्रिक ऑप्टिमाइजेशन में ही चला जाता है. ऑल्दो जो फील्ड्स मेडल था उन्होंने जो टूल्स यूज किए थे वो सिर्फ ज्योमेट्रिक ऑप्टिमाइजेशन के नहीं थे, उसमें कुछ फर्दर एडवांस किस्म के टूल्स उन्होंने यूज किए थे. द रीजन वाई ये जो प्रॉब्लम्स हैं अभी तक ये सॉल्व नहीं हो पाई थी क्योंकि अगर आप सिर्फ और सिर्फ ज्योमेट्रिक ऑप्टिमाइजेशन के तरफ ही रहें और वही कैलकुलस 3 की नौयत के ही टूल्स यूज करते रहें तो वो सॉल्यूशंस नहीं दे पाएंगे. The geometric optimization by the big umbrella is geometric optimization, but you would need heavier machinery to solve this problem, and well, maybe not this problem. You don't need. You've not Jin Bai didn't use any heavy machinery, but for particularly the sphere packing problem, उन्होंने जो थी ना सिर्फ ज्योमेट्रिक ऑप्टिमाइजेशन यूज नहीं की थी, उन्होंने और भी डिफरेंट टूल्स यूज किए थे जिसमें से कुछ आज ज्योमेट्री के भी थे।
राइट। और दूसरा मेरा जो एक मतलब जनरल एक क्वेश्चन है कि मतलब आपका कैसे इस प्रॉब्लम में इंटरेस्ट हुआ, क्योंकि मेरे ख्याल से ये आपका उस तरह से फॉर्मली पीएचडी वर्क नहीं था।
मैं अपने सुपरवाइजर के घर तो मुझे जो था ना एक सोफा मूव करना था एक जगह से दूसरी जगह तक, तो हमने बस वैसी बातों बातों में स्टार्ट की कि इसका क्या हल होगा और क्या हिसाब किताब होगा। तो देखा तो ऑलरेडी एक पुराना प्रॉब्लम था, तो उस वक्त से प्रॉब्लम पता चला कि कोई ना कोई एग्जिस्ट करता है। अब हमारे स्मार्टफोन्स इतने स्मार्ट है कि हमारी बातें सुन के फिर हमें उस हिसाब से डिफरेंट ब्लॉग पोस्ट वगैरह रिकमेंड करते रहते हैं। तो बस उधर से फिर इस प्रॉब्लम के बारे में चीजें जो थी और पढ़ना शुरू की, देखना शुरू की। जब सोल्यूशन आया तो मुझे मेरी नोटिफिकेशन में आ गई कि देखो दिस दिस माइट इंटरेस्ट यू। तो देखा तो वाकई इट वाज समथिंग दैट बेसिकली सॉल्व्ड द मूविंग सोफा प्रॉब्लम। अभी तक वो पेपर जो है पीयर रिव्यू नहीं हुआ हुआ, बट बाय एंड लार्ज लग रहा बातों से ये लग रहा है कि इट सीम्स सॉल्व। तो क्योंकि अभी ये चीज एक नई है, हॉट है, इसलिए मुझे ये था कि मैं इसको और देखूं और पढूं। और इनफैक्ट ये टॉक देने का मेरा मकसद ये था ताकि मैं पेपर अपने आप को जबरदस्ती पढ़वाऊं। आप एक चीज पढ़ते हो तो तभी वो क्या कहते हैं समझ आती है, लेकिन आप खुद से कहो कि मैं खुद से पढ़ूंगा तो फिर बंदा जो कहता है अच्छा वो 5 साल बीत जाते हैं, खत्म नहीं होती। अब मेरे पास इसी तरह आया था कि बस प्रैक्टिकल सिचुएशन से, और फिर आहिस्ता आहिस्ता डिफरेंट रिकमेंडेशन आना शुरू हुई। देखा कि दिस इज a big field, ignored field, really easy to get into, but really hard to solve.
ऑफ कोर्स मतलब स्टार्टिंग में बहुत क्लियर आपकी प्रेजेंटेशन थी, बट ऑफ कोर्स फिर जैसे आप हायर डिमेंशंस में जाएं तो जैसे आपने दिखाया कि नंबर ऑफ इक्वेशंस इंक्रीज करते रहेंगे और वो बट वन थिंग जो मैंने आई नोटिस्ड के फ्यूचरिस्टिक डिजाइन्स आपको मिल जाएंगे सोफाज के उसमें जो है एक ये फायदा हो सकता है इस प्रॉब्लम का कि बहुत इंटरेस्टिंग मतलब डिजाइन्स के फिर वो बनेंगे सोफाज, अगर ये कंडीशन हो कि हॉलवे से जो है वो गुजरना चाहिए। But
हाँ,
you're
काफी practical problem है। It's basically the idea is the sofa is too heavy to lift it, so you need to move it across the hallway, right? So क्या shape होनी चाहिए सोफे की? It's
नहीं, और ये बड़ा एक उस तरह से प्रॉब्लम है क्योंकि ये प्रैक्टिकली हम लोगों को आपने जैसे कहा ना कि ये मसला पेश आता है कि जब आप मतलब मैं जिससे रिलेट कर सकता हूँ कि जब आप सीढ़ियों से ऊपर लेके जा रहे होते सोफा, वो सीढ़ियों का अक्सर हमारे यहाँ डिजाइन ऐसा होता है कि एक पॉइंट पे आके आपको उसको वो इस तरह से टर्न करना पड़ता है, और
yes,
वो बहुत जो है वो टर्निंग जो है वो बहुत बड़ा मसला होता है, और वो एग्जैक्टली इसी वजह से कि मूविंग सोफा प्रॉब्लम में वो जो टर्निंग है
yes,
लीनियर तो आप चले ले जाएं उसको, बट वो उस पॉइंट पे बट एनीवे सो ऑडियंसेस इनकरेज के कोई आपका सवाल हो जरूर आप पूछें, चैट में भी लिख सकते हैं। और अगर डॉक्टर मोहसिन रज़ा हमें सुन रहे हैं तो वो हमारे पुराने एक म्यूचुअल एक हमारे साथी हैं, अगर वो कुछ कमेंट करना चाहें। उनको मैंने ज्वाइन करते हुए तो देखा था।
फिर भी शायद रोजा खुला लोग जो भी ना वो थोड़ा सा रिलैक्स कर रहे होंगे, तो इट्स ओके।
हाँ तो लेकिन ये कि इट वाज मुझे खुशी है कि चलें आपने अगर हमारे उस बहाने जो है वो इस प्रॉब्लम को पढ़ा, और आई एम एक्सट्रीमली ग्रेटफुल। और आई वुड रिक्वेस्ट के अगर ओके देयर इज अ क्वेश्चन फ्रॉम कदीर कुरैशी साहब। Can this approach be used to design more efficient bends in roads and train tracks?
Yes, it can. uh, अब इसमें फिर असम्पशन ये होगी कि आपने जो है ना गाड़ी की शेप या जो ट्रेन की शेप है ना वो फिक्स्ड है, और उसके हिसाब से फिर आप डिसाइड करेंगे कि फिर हॉल की क्या शेप होनी चाहिए। अब जो टूल्स जिन बाइक ने डेवलप किए मेरे खास वो डायरेक्ट एप्लीकेबल नहीं होंगे। उनको काफी तक मॉडिफाई करना पड़ेगा, लेकिन सवाल थोड़ा सा रिवर्स हो जाता है। ये कहता है कि ये फिक्स शेप है, बताओ कि किस हिसाब से हमें जो है टर्निंग एंगल डालना चाहिए रेलवे ट्रैक पे या क्या। अब उसमें अगर क्योंकि फिजिक्स एस्पेक्ट आ जाता है उसमें, फिर टर्निंग जब टर्निंग एंगल की बात आ जाती है तो फिर, और अगर आपने चीजें स्पीड से टर्न करवानी है तो उसमें फिर बैंकिंग एंगल की बात आ जाएगी, सेंट्रीपिटल फोर्स की बात आ जाएगी, उसमें फिर और कंसिडरेशन आ जाती हैं। बट जो जिन बाइक के टूल्स हैं वो डायरेक्टली एप्लीकेबल नहीं होंगे, वो काफी तक मॉडिफाई करना पड़ेगा और नई चीजें और डालनी पड़ेगी। So, अच्छे सवाल है। प्रैक्टिकल एक मैं पढ़ा था ब्लॉग पोस्ट में, किसी ने डाला था ऑनलाइन कि यार ये जो मूविंग सॉफ्ट प्रॉब्लम है वो लेंथ कॉन्ट्रैक्शन क्यों नहीं कंसिडर करता। तो अगर इन्फिनिट हम जो है वो हॉलवे कंसिडर करें तो लेंथ कॉन्ट्रैक्शन क्यों नहीं बीच में डाल रहे हैं? तो उसका जवाब ये बाय एंड लार्ज यही था कि इट्स अ ज्योमेट्रिक प्रॉब्लम, नॉट अ मूविंग ज्योमेट्रिक प्रॉब्लम। इट्स आप रोटेशन जो है वो रिलेटिविस्टिक स्पीड्स पे नहीं कर रहे, ऐसी स्पीड पे कर रहे जहाँ पे ये चीजें इग्नोर की जा सकती है। ऑब्वियसली एक सोफा अगर मूव करें तो आप आराम आराम से मूव करोगे, लेकिन जो जिन बाय की सोल्यूशन है ना, वो जो रोटेशंस है ना वो ली ग्रुप के थ्रू करवा रहा है। तो क्योंकि उनके मैकेनिज्म के अंदर चीज बिल्ट इन है कि अगर आपने रिलेटिविस्टिक स्पीड्स कंसिडर करनी है, कॉन्ट्रैक्शन कंसिडर करना है, वो आराम से डाल सकते हो। इन पर्टिकुलर अगर आपने बैंकिंग एंगल्स वगैरह डालने हैं ना, तो वो भी फिर आसानी से मैट्रिसेस के अंदर आराम से डाल सकते हैं। तो वो उसकी बस जिन बाय की वर्क मॉडिफाई करना पड़ेगा, बट आई थिंक इट कुड बी डन।
Thank you for the answer, Dr. Abdullah. Or there's one more question. Uh, Dr. R. M. Mirza ने पूछे कि why you did not consider the big wooden charpai?
That's a good question. Uh, I think चारपाई जो होती है वो थ्री डायमेंशनल हो जाएगी ना, तो
नहीं,
अगर तो
सोफा क्या थ्री डायमेंशनल है?
जी
इट्स जस्ट अ मैटर ऑफ कि चॉइस की बात है। मेरे ख्याल से वो सोफा भी थ्री डायमेंशनल है। यानी अच्छा, आपने शुरू में टू डायमेंशनल लिया है, ठीक है वो।
टू डायमेंशनल था, हाँ। तो चारपाई में फिर आपके पास वो आ जाती है ना, रेक्टेंगुलर शेप आ जाएगी। हम सिर्फ टॉप से फोकस करें तो रेक्टेंगुलर शेप आ जाएगी। तो अगर चारपाई हमारी स्क्वायर है तो वो एक मिनिमल सोफा बन जाएगा, एक्सेप्ट वो एक मिनिमल शेप बन जाएगी। तो उसको फिर आप मॉडिफाई करें, सेमी सर्कुलर चारपाई करना है, या तो फिर इस तरह की हाईली इनएफिशिएंट किस्म की चारपाई डालें जिसमें आप करोटे नहीं बदल सकते। तो कुछ ये भी इसका मतलब हो सकता है।
राइट, राइट। चलें, the audience is very much encouraged to ask questions. Or meanwhile, I'll request Khalil Raza Saab if he wants to, say something about the talk, and he's the
Thank you, Imran Saab. Thank you, Dr. Abdullah, for this very engaging and insightful talk. So, on behalf of ECO Science Foundation, my gratitude to you, and we
Happy
look
to be here.
forward to hosting similar insightful talks in the future as well. And
Sure.
we look forward to having you one more time in the
Of
future as
course.
well.
Look, happy to
Yeah.
be of service.
So it's interesting. But एक चीज मैं जो सोच रहा था कि फॉर इंस्टेंस जब विंड टर्बिन्स, क्योंकि उनके बड़ी लार्ज स्पेस लेंथी होते हैं, जब उनको मूव करना होता होगा from spaces, can your approach be used to address those moving challenges for wind turbines या fuselage large aircrafts के?
राइट, ये जो इनिशियल प्रॉब्लम था वो उसकी अल्टीमेटली दूसरी फ्रेजिंग यही थी ना कि would be to find the longest rigid convex thin rod which can move through above hallway. So essentially आपकी जो wind turbines है, अगर आप उनको इमेजिन करें कि पता से लंबा सा रॉड है, तो उसकी तरफ भी अप्लाई हो सके इसकी मैथ। ऑल्दो जो सॉल्यूशंस मिले हैं वो उसमें इस तरह की शेप्स नहीं कंसिडर की, वो अल्टीमेटली सोफे तक ही बात की गई है। लेकिन उसमें I would guess कि instead of rotating the hallway, आप you not just rotating the hallway but you're also moving the hallway, क्योंकि आपने जो वो रॉड है उसको सिर्फ रोटेट नहीं करना, तो उसके साथ थोड़ा सा मूव भी कराना पड़ता है। तो यस, मतलब जो स्टार्टिंग पॉइंट इस प्रॉब्लम का था वो यही था कि आप शेप स्क्वायर ले रहे हैं या रॉड ले रहे हैं, दोनों को क्या शेप होनी चाहिए, क्या मैक्सिमम उसमें कहाँ का कर्व्स आना चाहिए। तो the answer to your question is yes, there would be another practical application. We will just need to, find the actual solution using the tools that we have so far. But yeah.
Right. Thanks for the feedback. So that's all, Imran Saab, from my side.
right. Thank you, Khalil Saab. And so I would request Ms. Hafsa कि एक तो feedback form उन्होंने share करी. So Hafsa, if you close it formally, please.
Yeah, okay. Thank you so much, Dr. Malik, for such an interesting talk, and thank you for everybody for joining. And before we conclude, as Imran said, the participants are requested to fill out our feedback form, and you can stay connected with us by following our Facebook page for updates on upcoming webinars. Thank you so much, everyone.
All right. Allah Hafiz. Goodbye.
Allah.